So up next, we've got Christian Zur from the AEMC. He is the Energy Policy Director there, and will be speaking about the upcoming rule change on system strength. Take it away, Christian.
Thanks, Carl. Hello, everyone. So yeah, today, excuse me, as Carl mentioned, I'll be talking about the draft rule determination that the AEMC has just made on system strength. This is as follows: a rule change request from Transgrid and builds on the work that the AEMC did last year on system strength. So at a high level, what this rule change is about is the proactive provision of system strength, which is a service that's really critical for the stable operation of IBR on the power system, and is therefore central to the decarbonisation of the NEM. We put frameworks, or the AEMC put frameworks in place to deliver this service back in 2017. I think it's fair to say those frameworks, which include the do no harm provisions, which I'm sure some of you are familiar with, really haven't worked all that well. And so these new frameworks that we've proposed in the draft determination are really designed to build on those frameworks in 2017 and try to do things more effectively. Relevance to today is we consider the grid forming inverters may very well play a central role in providing or in strengthening the system generally. Firstly, by potentially reducing the demand of IBR generators for system strength by managing inverter-driven instability, but also by actively providing sources of system strength, by actively contributing to the stabilisation of the voltage waveform, which is what system strength fundamentally is. So just very quickly, the work that the AEMC is doing on system strength is is very closely related to the work that the ESB is progressing. There are 4 key essential system services: operating reserves and resource adequacy, frequency control, then inertia, and then the 4th one is system strength, which is about IBR-driven instability or IBR-related instability, as well as the provision of minimum fault levels. And the AEMC is progressing that work through its review and then this rule change. So there are 3 key components to the draft rule that was made a couple of weeks ago now. And these are consistent with the recommendations that we made at a higher level last year in our review of system strength frameworks. So we've divided up into, I suppose, what we're calling the supply side, the demand side, and a coordination mechanism, being the pointy-headed economists that we tend to be, or that we do tend to be at the AEMC. So on the supply side, really this is about the proactive provision of system strength. So you have sufficient volumes of this critical service where it's needed, at the right locations, and most importantly, that it's there when it's needed. So you don't get the kinds of bottlenecks that we've seen with system strength over the last couple of years. So the fundamental component of the supply side is a TNSP-led procurement or provision of system strength. And this will basically take the form of a system standard that TNSPs will be required to plan for and meet. And a critical input into this standard will be AEMO's projections of IBR connections in the future. And basically, TNSPs will be required to work closely with AEMO to proactively provide the needed volumes of system strength so that these projected levels of IBR can be expected to operate stably under normal conditions. So this will be a prescribed transmission service, which means it's rolled into the RAB. But as we'll explain later, it is also then partly recovered from connecting generators. The second component is the demand side, which takes the form of a couple of new access standards that will apply to IBR generation, as well as to load and MNSPs. These new access standards really are designed, I suppose, as a backstop, the security backstop, to ensure that the system stays as strong as it can be. And it also ensures that connecting parties make efficient use of this scarce and very valuable resource that we describe as system strength, or that we call system strength. The third component is what we're calling a coordination mechanism, and really at its core, this system strength mitigation requirement is a choice that connecting IBR will face. And fundamentally, the choice is to either pay a charge and make use of the centralised provision of system strength, or to self-remediate and to bring your own system strength. And what it means is that the connecting parties will pay for some of the provision of system strength. Really quickly, key benefits: proactive provision of system strength. Really, one of the key things we're looking to address here are the quite significant bottlenecks that have occurred recently with connection of new generation, as well as curtailment. So, by having, by providing connecting parties with a choice about whether to pay the charge or bring their own system strength, we feel that should provide greater certainty and clarity in the connection process and hopefully speed things up. We think that by enhancing scale, scope and operational efficiencies, we ought to be able to get system strength at lower costs. Having one procurer for the service means that it should be provided at a lower cost for customers. And then also addressing the reactivity of the existing frameworks. It's been a key problem with the existing mechanisms is that system strength hasn't been brought when and where it's needed. So a purposefully proactive mechanism hopefully will address that. So into the details, the new system strength requirement, the supply side sets a new system strength standard. Now, fundamentally, there are two parts of this standard. There is a minimum level for system stability, which is broadly equivalent to the existing minimum frameworks for fault level or for fault current. The key part of this is that you have sufficient levels of fault current so that protection equipment can function effectively, clear faults and keep the system safe and stable. And obviously this also flows over and has an impact on the general, should we call it kind of backbone or baseline levels of service that's needed to maintain general system stability, recognising that system stability is a broader question than system strength, at least as we've defined it. Probably the more interesting part though of the new standard is that it actually requires TNSPs to provide an efficient level of system strength, which is this top part. And really, this is all about keeping the voltage waveform stable so that wind, solar, or basically IBR can connect and remain stably or operate stably in the system. And this is all about supporting the efficient level of IBR, which, as described before, is that which is forecast by AEMO through the ISP and then calibrated against TNSP's own understanding of the volumes that are connecting. So really the standard is all about TNSPs proactively providing levels of system strength so that those expected volumes of IBR can operate stably. The second component of what we're doing is the system strength charge or system strength mitigation requirement. Three components of the charge: the system strength price, which is developed by the TNSP, providing system strength in accordance with guidelines from the AER. And that's really based on the long run incremental cost of providing system strength. The system strength locational factor, which is all about, well, reflects the fact that system strength is a highly locational service, and that'll change according to where a generator elects to locate. The closer you are to a node where system strength is being provided by the TNSP, the lower the charge will be. Now, both of these components will try to balance the need for predictability again with flexibility, and so that both of these components are fixed for a 5-year period. The third part of the charge is a system strength quantity, which can be controlled by the connecting generator. And that's really about how much system strength the individual plant actually requires. And as mentioned, the generator or the connecting plant can actually change that by altering its plant as needed. So fundamentally, the system strength, this SSMR, system strength mitigation requirement, gives generators a choice. They can either pay the charge and make use of that centralised provision of system strength, and that means that they only need to go through the PIA process rather than the full impact assessment process, which we understand should make things a lot faster, a lot simpler for those generators looking to connect and pay the charge. If the generator elects to self-remediate, it does need to go through the existing FIA process, undertake system strength remediation works and/or contract with another party. Two new access standards. I won't go through these in great detail. A minimum short circuit ratio requirement for stable operation down to SCR3. as well as a requirement on minimum vector shift protection obligations. I'm happy to talk further about these offline, but thought I might skip to the main things that I think people are interested in to talk about today. So grid-forming inverters, we think, offer a great deal of potential when it comes to the provision of system strength. I mean, as Chris talked about here, we think that systems or grid-forming inverters may very well appear or may very well provide a lower cost alternative to Syncon build. It can also allow IBR to value stack, to both reduce their own demand for system strength, potentially reducing that third component of the charge to zero, and therefore avoid having to pay a charge. It also means that the generator potentially could offer network support agreements and actually help the TNSP in the proactive provision of system strength by providing their service to help to stabilise the voltage waveform. Now, obviously, there's still a bit of work to be done to actually allow this to occur. As Chris mentioned, there's a lot of work to be done thinking about how to standardise such a product to perhaps better define the nature of the service that's being procured. But at this stage in the draft determination, we've left it reasonably open to say that the TNSP can engage with any party who can demonstrate, in accordance with AEMO's System Strength Impact Assessment Guidelines, which is a document that AEMO sets up about how to provide system strength, that any party that can demonstrate they can support the TNSP can then sell those services to the TNSP. Above and beyond system strength, there are probably a number of areas where the regulatory frameworks can or probably or may require some development in the near term to fully unlock the capability of grid-forming inverters. The first is the access standards, which underpin the generator performance standards, which is a process that every connecting party goes through when connecting to the NEM. Now, those existing standards were really developed around synchronous machines, and then we adapted or developed them a bit further in 2018 to reflect some of the capabilities really of grid-following inverters, current source inverters. So I guess the question that we have to think now is, do we need new standards to account for the additional capabilities of grid-forming inverters? Equally, though, could we just rely on or leave things as they are? If we say the grid-forming inverters can also be described as virtual synchronous machines and do everything that a synchronous machine did, can we in fact leave the access standards as they have been? Perhaps that's equivalent. Anyway, in any case, there's further work to be done there. A second area to be looked at is, I suppose, system operation, the philosophy of system operation, as well as AEMO's security obligations. How do we actually operate a system? How does AEMO actually operate a system that has large volumes of grid-forming inverters? You have to have presumably some sort of philosophy where you've got leaders and followers, some that are setting the reference voltage and others that are following. Or if you have everyone forming the reference voltage, you need some equivalent of a droop that you currently, or like droop settings that you currently have for synchronous machines. So does this look the same as the existing philosophy for system operation, or does it need to change? This is obviously a question for AEMO to answer fundamentally, but given all of AEMO's system security obligations are set out in the rules, it's likely that the AMC will need to have a think about this as well. I think, as Chris mentioned in his presentation, and as I'm sure we'll hear more of from the presentations later on today, grid-forming inverters also have a great potential for new services. In particular, system restoration, system restart services, I think there's a huge amount of potential there. I think I've heard the capabilities of grid-forming inverters described as graceful decay. That the ability to form small islands might help prevent a full cascading failure, perhaps as a stage between UFLS and SRAS activation. So I think there's a huge amount of potential there. Now, we began to unlock the potential of that in a rule change made in 2019, where we gave AEMO the ability to define new system restoration support services. And we think that, and I think that grid-forming inverters really have a lot of potential to offer those kinds of services, which might help in those initial stages of a system restoration. Finally, there is work being done by the ESB and the AMC, obviously working as part of the ESB through what's known as the System Security Mechanism, or SSM. Now, look, currently the SSM is looking at how we might procure kind of combinations of synchronous machines to maintain underlying system stability and operability. I think there's a lot of potential, though, in that mechanism to go further, and I think grid-forming inverters offer a huge amount of potential there. Can we move to a world where instead of procuring combinations of synchronous machines, we instead procure combinations of grid-forming inverters to provide that underlying grid stability? And I think then another question that raises is, do you still need any form of aheadness, as has been prosecuted, through the ESB's process? If you're no longer relying on big thermal units with long start times and high unit commitment costs, then what does that mean for the need for aheadness? That is all I was going to talk about today. It's a bit of a whistle-stop tour of a lot. Really looking forward to answering any questions. Thank you.
Thanks, Christian. Again, I think some really timely and important work that's going on, and some clear synergies with what AIM are hoping to do as well. So now I'd like to hand over to Dan Starrick, who's an investment director in our business development and transactions team here at ARENA, and he'll moderate the Q&A session, which thankfully we've got a little bit more time for, because Chris and Christian have gotten through quite quickly. So I'll hand over to Dan.
Fantastic. Thanks, Carl, and thanks, Chris and Christian, for some really good introductory presentations, which I think set the scene really well for the second half, and as we get into some of the projects that we're going to be talking about. To sort of set the scene at a slightly higher level before we get into some very technical questions that are coming through in the Q&A, so no surprises there. I think that the scene that's been set here is that the technology is developing fast. As we know, that's what this sort of technology does. It sort of moves quite quickly, probably ahead of regulations. We've got the regs developing in parallel. We're talking about 2025 and really getting ready for that sort of next phase. And the need is growing, and renewables are growing, which is obviously great, but creating challenges. So question to maybe Chris first, and then to Christian, kind of how important are advanced inverters in this context? We've got technology coming through fast. The regulations might take a while to really kind of sort of settle into sort of what the technology can do. Can you just give us your sense of how important you think this area is? And I guess obviously very complex, but how important is it that we get this right and work together to solve these challenges?
Yeah, look, I think very important is the short answer there. I mean, there is going to be a long-term role for advanced inverters in the NEM. I would hope that they're able to comprehensively provide for all of those four applications that we detailed today, at scale, and ultimately support the system in the absence of synchronous machines at certain periods of the day in the near future. In terms of how we manage the pace, and the fact that this technology, I certainly don't want anyone to think through my presentation that we see this as early days technology. This is very much established and very much being built today, and I think what we want to do is to try to capture that and recognise that there will be latent capability in some of this equipment that's going in, and building for the system of the future while those rules are being developed around it. Now that's a challenge from a revenue perspective, obviously, if there aren't sort of services markets or anything like that in existence to compensate for people installing equipment that may be more complex. Then we need a way to get over some of those hurdles today, such that what we're building is capable of the necessary levels of grid forming that we're going to need tomorrow. That's, I guess, a short tour.
Thanks, Chris. And then sort of slightly kind of amended question for Christian. I guess, given that the technology is so complex and defining system strength is so multifaceted, what sort of challenges does that create for the regulatory environment you're working towards, where you can see that different technologies will say, well, what we can provide is not quite the definition that you're giving us, and I guess that you've given AEMO the job of defining the standard, but how does that work in an environment where the technology and the services are quite multifaceted?
Yeah, iteratively. I mean, really, it's the end of the day, isn't it? As you said, Dan, the development of just what system strength is took us about 1.5 years. Well, maybe a year, I suppose. You know, this is an amorphous concept. It's somewhat, I won't blow my own trumpet too much, but it's world leading. I mean, this is not really a term that is well understood, you know, around the world. So it is really difficult to first even just define the nature of the problem. It took us quite a while to do so. And there are ongoing discussions about, well, how does system strength relate to broader system stability? Where are the overlaps? You know, how are these two things, you know, related? So it takes time to make rules that are that reflect the physics, particularly as the physics itself and the understanding of the physics is developing, you know, or is in development, you know, by the engineers, by industry. So it has to be done in an iterative fashion. And I mean, I think what you'll see, what you've already seen from the ANC is we make rules. Hey, they don't turn out to be perfect. So then we adapt them and we develop new rules to try to reflect the, you know, the learning process. And I think that sort of iterative process, you know, with the AMC working with ESB, AAR, AMO is going to have to continue, you know, so that we can adapt these rules as the technology, you know, sort of changes so rapidly.
Thanks. Okay, well, let's move into some of the more specific and technical questions. The first one came through from Steve Wilson. And the question is, can you elaborate on the need for advanced inverters to have high fault current for SRAS, and whether consideration is being given to inverters instead providing a soft start voltage ramp up of transmission elements with group protection used to manage lower fault currents for protection during a black start? So yeah, I think that's definitely one for Chris Mock. Hopefully
it's actually a really good question, and I think it highlights probably some poor wording on my part on those slides. Is that, you know, the system today, black starting a system with synchronous units requires a large amount of fault current, right, to energize transmission assets that are black, and whether that's from a top down or a bottom up philosophy, that's the same challenge. That example that I mentioned about the Scotland to Norway interconnector, part of that process, part of that project included testing for SRAS capability, and it's one of the case studies in our report. And they achieved that capability through the use of soft start technology, right, where they essentially ramp up the voltage slowly over time to avoid these rapid changes in operating conditions that lead to these high current demands. And, you know, ultimately that's a really good example of where advanced inverters have the edge in terms of flexibility. You can have a fine-grained control over their output to meet the needs of the power system in that instant, rather than everything being kind of inherently coupled through the electromechanics. So yeah, that I think is a very you know, a very relevant question for SRAS. I think that, you know, that we pointed out that there are very few SRAS units currently, and largely that is due to the cost and the technology required to provide that functionality. But if it was really cheap and if it could be deployed at scale in a diffused manner across the NEM, that just gives us so many more options. So you're really exciting space.
Okay, thanks. And the next one for Christian is around the role of system strength in the distribution network. So how would the sort of TNSP regime sort of flow down to the DNSPs in managing system strength at that level?
Yeah, look, I mean, that's a question that's been raised by a lot of stakeholders, and you know, and fair enough. Look, the approach that we've taken in the draft determination is to have one provider of system strength in a region, and the reason for that is that having multiple providers of this service in a region, we think, could lead to well, a lack of coordination, which at the end of the day could drive up prices for, ultimately drive up costs for consumers. So the approach we've taken is there's one provider, that's the system strength service provider, which is typically the jurisdictional planning body, which in every jurisdiction of the NEM is one of is a TNSP. So that means by inference that the DNSP won't be required to meet the standard and won't be a system strength service provider. Two things to moderate that. Firstly, the joint planning processes we consider should allow for the efficient consideration of distribution network needs for system strength, given that most of the large-scale IBR is connecting on the sort of sub-transmission network. We feel that provision of system strength by the TNSP close to the boundaries of the two networks ought to be sufficient to provide system strength needs within the distribution networks. But look, acknowledge this is a live issue. A lot of stakeholders feel very strongly about this, so really keen to get feedback to the draft determination and submissions on this one. The other point I'd make is there is nothing preventing DNSPs from offering system strength as a negotiated or a competitive, non-regulated service, while the rules don't allow for them to include it as a prescribed service and roll it into the lab. There's nothing preventing the DNSPs from offering this as a competitive service, just as there's nothing preventing TNSPs from offering this as a competitive service outside of the nodes that have been formally declared where it's provided as a prescribed service. And we saw indicative approaches towards this by PowerLink, thinking about providing system strength as a service. So there are a few kind of nuances to that question, but recognise that it's one that a lot of stakeholders feel pretty strongly about. So as I said, very keen to get detailed feedback on that one in submissions to the draft determination.
Okay, I think a follow-up question that's reflected in a few of the questions coming through. If I'm a project with an advanced inverter that's providing system strength, and I guess, on one hand, I guess that means that I'm self-remediating. Can you talk through how you would see my mechanisms to provide system strength back to the network or to other parties? Is there sort of some thoughts around that?
So we talked before about the regulatory frameworks trying to keep pace with what AEMO is doing and what's happening around across the board. So look, I guess the issue here is that we don't yet have, and I'm sure Chris's paper, AEMO's paper coming up in July will really start the process for this, but we don't really have a clear definition of what a grid forming service, an advanced inverter service is. So what we've done in the draft rule is kind of left it open and said, look, we expect that once these capabilities are more sort of described on a physical basis by AEMO, then it will be open to, we've left it open to the TNSP to strike agreements with parties that have grid forming IBR, grid forming inverters to provide system strength services. But because the physical definition of what a grid forming inverter isn't there yet, we haven't sort of been able to kind of give a great deal more prescription in the rules. In terms of the demand of a generator connecting with, or demand for system strength, and therefore their exposure to a charge, our view is that through AEMO's system strength impact assessment guidelines, AEMO will define how it is a party with a grid forming inverter would actually incur or create a need for system strength. It's our expectation that AEMO will be able to define these grid forming inverters as effectively meaning the demand for system strength is zero. So if you remember that charge kind of equation that I put up before, the third component of that is the system strength quantity or demand for system strength. We'd expect that parties with a grid forming inverter, for them, that component of the charge would be zero, therefore rendering the entire charge zero for a generator looking to connect.
Okay, one for Chris Mock. We got the term algorithms in this question. I think the question is around, different grid forming inverters will have different algorithms in terms of how they operate and respond. And the question is, would there be a requirement for the manufacturers to explain their algorithms in terms of managing concerns around interactions, or would this be prevented by IP laws? I guess, how do we understand some of the black box questions and manage those issues?
Indeed, right. And whether or not an understanding of the algorithm or demonstration of the algorithm is needed, I think is the question there. And ultimately, we're attempting to go out there, as Christian said, and sort of define services and applications for these, rather than saying the device needs to work like this, has this algorithm, has this exact functionality. However, we need to be able to model them. And ultimately, especially in these sort of early days with deploying grid forming inverters at scale, we really do need to be able to prove these things on desktop studies before we start to roll them out in practice and test on the live system. So the IP constraints around being able to access those models is very real, and it's certainly something that I think we're going to need to continue to understand firstly how AEMO can get access to those to perform our own modelling, and secondly how can other participants in the system do their own modelling, knowing that there are devices which will interact with theirs in these specific ways due to the varying algorithms available.
Okay, great. Conscious that we're getting towards the end of time, and there's just some really good technical questions, which I think was partly dealt with, but I think probably best to deal with them maybe post the session. But I guess one final question to bring us into the next phase, which is, I guess, how important do you think, I know this is a Dorothy Dixer probably, but how important do you think these ARENA funded projects are that we've already got are in sort of helping you guys as the regulators sort of tackle these really difficult questions? And ultimately, what more do we need to do on the theme of knowledge sharing and collaboration to help us deal with these really, really challenging questions?
Chris, do you want to go first, or?
You off you go.
I think cool, mate. So yeah, no, look, huge value. I mean, as I said, the understanding of what system strength is, from my perspective on my role, is it's still, very in development, right? So to the extent that there are trials going on out there, and I look to, I believe, PowerLink are doing some work there in particular, in terms of what batteries can do, but also what collective retuning of inverters can do. Those kinds of trials are invaluable because they give us an insight into what the future could look like. And you can design rules then around where you think the physics, where you think the system and the industry are actually going. So absolutely invaluable. And as we've worked through the system strength rule change, we've had a lot of conversations with ARENA and with the parties involved in these trials. And it's really helped us actually sort of turn the abstract theory into something more practical and applied. So I think they're extremely valuable.
I think it's important as well to note that some of the services delivered by Advanced Inverters are actually fairly comprehensively understood in terms of their capability, and maybe we haven't got the firm definition on what system strength from one of these devices is going to look like, but we're pretty confident that it will work, as opposed to, say, lower TRL services such as stabilizing a regional island, how do multiple advanced inverters work with each other, or providing primary frequency response at a distance. How do these sort of wide scale studies feed into our decision making on future use of these services? And so there's two buckets, I think. If ARENA can help with the advancing those low TRL services so that we can bring them up to the point where we understand them and can start to specify and commission them, as well as understanding, well, how do we get the known services out there and built today while we develop the rules iteratively, as Christian pointed out.
Okay, great. Well, I think that's a pretty good segue into the next session. So back to you, Carl.
Thanks, Dan, and again, thanks, Christian and Chris. So we'll download those questions that weren't answered and pass them on, I think. So up next, we'll have a session with a variety of our projects. I'm really excited about this one. So I'd first like to introduce Sachin Goyal, who's a manager, power system performance and connections at PowerLink, to talk about some of their recent work. Over to you, Sachin.
Carl, can you hear me? I'm just trying to get the presentation up and running. Please let me know when it's...
I think you're all good now.
Okay, good. Thank you, Carl. Morning, everyone. My name is Sachin, and I'll be presenting as part of this presentation the project that PowerLink received funding for in conjunction with its project partners, like Hydro and Sun Metals. And as part of this project, there were mainly three parts of this project. Hang on a second, why it's changing. That's okay. So there were three parts of this project. First one was to give a general understanding of system strength and how can we look into the options of having a centralized solution versus project-specific solutions. So that was the first part, and the report is on ARENA website. And the second part of this project was to perform the detailed studies. When I say detailed studies, I'm talking about EMT domain studies, PSCAD studies, and prove that a synchronous condenser is used as a centralized solution does work, and what are the pros and cons of that. In the third part, which is this presentation based on, is to further explore the possibilities of using grid forming inverters with battery, and how grid forming technology can help us dealing with some of the challenges of system strength and the weak grid, and host more renewables in the grid. So I'll be presenting some case studies, results, and the challenges with the grid forming technologies. To give you some of the background of this study, what we did as part of this project, we invited some. Sorry, this is running up. So as part of this project, we invited few manufacturers to submit their plant-specific model. So the thing that I want to highlight here, this study was not done based on a generic model of a grid forming inverter. It was done based on a manufacturer, OEM specific model. And from network point of view, the Queensland network was used to test the capabilities of grid forming inverters and to identify the benefits of grid forming capabilities. So it's quite close to what we would do for a connection project. However, at the same time, I would also want to inform this group that the results presented in these studies are for this example, but cannot be directly translated into any project. When a project comes up, we'll have to do project-specific, site-specific studies for that project. Okay, now what is grid forming inverter? And just very at high level, because there has been a lot of confusion on grid forming, what grid forming means. And when we talk grid forming here, we are really focusing on the inverter that doesn't really rely on grid voltage to produce its own waveform, right? It can produce its own independent waveform, so which means it doesn't have a phase lock loop. It can also provide some synthetic inertia to the system, and in a simple term, it should be able to reflect the capabilities of a synchronous generators to some extent. That's what we mean by a grid forming. And the differentiation between grid forming and grid following here is that we are not relying on a grid to create the reference here. Now, in terms of the case study, what you see here is a simple representation of the part of Queensland network. And what we did first, we connected a couple of inverter-based resources, which are grid following. And we are showing, okay, if we connect some renewables, then there is a problem. And then what we did, let's connect a synchronous condenser and see if synchronous condenser can fix some of those problems. And in the third case, what we did, we took the synchronous condenser out and put a grid forming battery and compared that, okay, can grid forming battery solve the problem similar or in some cases better than a synchronous condenser. So in this network, what you see, this represents the 275 kV network, and in parallel, there is a 132 kV network. And in results, when I'll show you, I'll talk more about the impacts of 275 kV and 132 kV. Right. So what we see here is, okay, when we connect a couple of renewable plants without any support, after a contingency, we see some control interactions. And those control interactions are not new to NEM. Some of you are quite aware of those 8 to 10 hertz oscillations in NEM. We have seen those in Queensland, Victoria, and everywhere in NEMs, right? So this is exactly what we see here. And then we connected a synchronous condenser on to a close by bus, and then see, okay, can synchronous condenser help mitigating those control interactions, which are those 8 to 10 hertz oscillations. And as you can see from results here, synchronous condenser is well capable of mitigating those control interactions. What we did then, we took the synchronous condenser out and put a grid forming battery here. And obviously, the tuning of battery is required as it's required for any other project, including synchronous condenser. But what I'm showing you here is that a battery operated in a grid forming mode can also solve the control interactions problem, which was solved by synchronous condenser. The other point I would like to mention here, we did further tuning of the grid forming battery. And what we found that if we put enough efforts behind the tuning of the plant, the size of the battery can be optimized, or in this case, we were able to reduce the required size by half. What it means, the initial studies were done by 100 megawatt battery, and synchronous condenser size was similar capacity in MVA. It was around 120 MVA. But when we tune some of the controller parameters of the grid forming battery, even with the 50 megawatt battery, we could get the satisfactory results. So that highlights the importance of the tuning of the plant for project specific, site specific. Now, so that was the one part of dealing with the control interactions. Then we further looked at that, okay, can we use battery to help us maximizing the hosting capacity? And when we say hosting capacity, the transient and voltage stability have always been the bottleneck of the network and will continue to be. And so what we explored here, that, okay, can we really use this technology to help us revealing some of the capacity from voltage and transient stability point of view. And this is the same network. So what we observed that, okay, if we open these 275 kV lines, which basically decouples this part of the network from rest of the grid, from 275 kV grid, it's only remain connected through 132 kV, which is very, very weak part. It becomes quite weak. In fact, the short circuit ratio in this part of the network goes below 2, right? So the stability of grid following inverters is quite compromised. So if we don't have any remediation here, and when we trip these two lines, we have no other options than just tripping two renewable plants, because they will not be stable. Now, when we trip these two plants, it creates a transient stability problem, because, okay, first I'll go, if we did not trip these two plants, power will start flowing through 132 kV network, and it goes through high impedance network and creates the transient stability and voltage stability, right? When we trip these two plants, what it causes, it basically, if you look at the problem, we trip two lines, and then as a result of this, then we are forcing two plants to trip. So the overall disturbance in the network is even bigger. And what it does, it destabilizes the other plants connected in that area, which are other small synchronous generators. And if there was a synchronous condenser, it will do to synchronous condenser as well. So the point to be noted here is that while synchronous condenser fixes the problem, we should not forget it is also a rotating machine, and it has its own challenges. And if disturbance is too big, then it can have some stability problem itself. So what we had to do, we had to reduce the output of these plants by 80% before even a contingency, so that we can minimize the disturbance and we can trip. So there was one solution. Okay, rather than running plants at 100%, we'll always put them at 80%, and then when this these two feeder trips, we'll trip these two plants and network will survive. But definitely, I'm sure you can appreciate it's not a preferred option. We don't want to run plants at 80% all the time. So then what we did, we put a synchronous condenser here, and then see, okay, what synchronous condenser do in this space. So because synchronous condenser provides some voltage support here, so it definitely helped to some extent. But after tripping these 2 lines, we still had to trip one of the plant. We could not let both the plants survive, because again, the power which was flowing through this high impedance line was too much and was causing the network to go unstable. Therefore, post-fault, we had to trip one of the plant for network to survive. And those are the results we see after connecting a synchronous condenser, that yes, voltage recovers and system survives. But then we continued our journey with the grid forming battery here. And we looked at, okay, what grid forming battery can do. One of the benefit of the battery is, we can force it to change its mode from discharging to charging mode. And what it did in this space, that after the fault, if we forced battery to absorb the power, it would, I'll go back to slide 1 here. So if battery is connected here, and then after a fault, we forced battery to go from discharging mode to fully charging mode, which absorbed the power from these renewable plants, right? And bought some time for these renewable plants to gradually reduce their output and maintain the system stability, because the overall power which was flowing from this part of the network was controlled, and hence we managed to keep the system stable. Right. So now, can this be done with grid following batteries? This particular functionality of changing the mode from discharging to charging or charging to discharging, yes, we can do with grid following batteries as well. But as I said before, when we trip 2 lines, 275 kV, the short circuit ratio becomes quite weak. And if it was a grid following battery, the battery will go unstable itself, right? So it won't be helpful. So therefore, in this particular application, it's important for us to use this functionality of battery, that it's grid forming. Otherwise, it will not be able to survive these conditions. And the time that this battery bought for us, in that time, we managed to reduce the output of the renewables by 50%, and system survived. What these slides are showing, that if we don't have this coordination of renewables reducing the active power and battery changing its mode, then again, system will not work. What it emphasized the importance of the coordination of the plants, that, okay, if we go back to the original mode of discharging, so fault happened here, and we forced battery to go into the charging mode, but without reducing the active power from renewable plants, if we force battery to again pump the power, system will go unstable again, because power starts flowing through the high impedance lines. And that highlights the importance of coordination in the area with the other plants to maximize the benefit of a particular plant and the network hosting capacity. So those are the test cases that we went through as part of this project. And obviously, you would appreciate that that there's nothing called a silver bullet, and so grid forming inverters also come up with their own challenges. And one of the challenges is that, okay, for anything to be grid forming, there's a certain requirement for oversizing, and it depends on different parameters and what application we want to use grid forming batteries for. And to our best knowledge at the moment, grid forming is only available for batteries, either fully battery or part battery, part solar, or I'm personally not aware of a wind farm, but yes, solar and batteries. But some battery is required for inverters to work as a grid forming at the moment. Technology is developing, it may change in future. As I said before, the tuning of the plant becomes more critical to maximize the benefit. And then there are some limitations with during the fault, then how to limit the current now of the inverter, because at the end of the day, there are IGBTs connected, and we do not want them to blow if too much current flow through them. And I'm not the expert in that, but that's the knowledge that we got from different manufacturers. And I'm sure others in this group can talk more about that. And the other thing that I want to highlight here, that because these grid forming batteries, we are trying to emulate synchronous generators, then there's a possibility that they will be prone to a small signal instabilities because, as similar to a synchronous generators. So that is something that we need to be aware of. And then we connect with multiple grid forming battery in an area. We just need to be quite vigilant of that. Okay, what other instabilities we may create and how do we prepare ourselves for those? So as concluding my presentation, we're quite comfortable saying that grid forming batteries can play very constructive roles enabling renewables and supporting the operation of power systems. In this particular example, what we demonstrated that 100 megawatt of battery can support about 300 megawatt of IBR plants. Obviously, a thoughtful deployment of grid forming batteries with other technologies is very critical for transition. And given the positive findings so far, the logical step would be to get a project up and running. Thank you so much.
Thank you, Sachin, for that very interesting presentation. We'll have that final PowerLink report published in the coming weeks, and we're looking forward to that being publicly available. Some really important findings in there. We'll leave questions to the end, but feel free to keep putting those in there to particular presenters, and then we'll get to those once the other projects are presented. So I'd like to pass on now to Garth Heron, who is the Head of Development for Australia for Neoen.
Hi, Carl.
Thank you.
Hi, and I've got Joseph Tadich as well with me, who's heading up engineering at Tesla. Joseph, can you hear us?
Yeah, can you guys? Hi all.
All right, I'm going to have a crack at sharing my screen. It wasn't working earlier, but I've tried to fix it. Can anyone see that now?
That's looking good.
All right, very good. Well, thank you very much, Carl, and to the other presenters today. Sachin, it was great to see that that last trial and some results from that. So today, Neoen and Tesla, we're presenting some synthetic inertia trial results from Hornsdale Power Reserve expansion. We have some slides to show just around the background at what the difference between the synthetic inertia we're providing and traditional inertia looks like. But more importantly, the results, and we'll present some of the challenges we're facing as well as we roll through this this project. So just as background, we're using a mode in the Tesla inverters that are installed at Hornsdale Power Reserve that mimics the behavior of a synchronous generator. So essentially, this is called virtual machine mode. And it's got a couple of components to it. Really what it's designed to do is mimic the behavior of a heavy spinning generator. And it does that by producing an active power response proportional to the rate of change of frequency. So where we see the rate of change of frequency high, there's an active power response to it. And then there's also a reactive current response that's produced in response to a change of voltage. What's interesting about this system is that it only kicks in. It's only designed to kick in when the system becomes unstable. So under normal system stable conditions, the inverter behavior is driven by the current source component only. So maybe just to talk about the difference between the synthetic inertia we're providing and traditional inertia. So it comes down to the physics. So with traditional inertia, you have a big heavy machine, and it's spinning, and it's providing a natural power exchange when there's a rotor acceleration due to the change of frequency that experiencing. With virtual inertia, we're able to provide a synthetic version of that by using a microprocessor control to mimic that behavior. And that gives us a couple of advantages. The big one is we can change the inertial constant, or we can basically change the weight of the machine and what that looks like in the grid. The other big pro is that we're able to only move into this mode when it's necessary. So what it means is you don't have to be dragging around all of that inertia, for instance, when you're trying to recover from a system event. There is one major disadvantage, of course, and that comes down to the amount of current you can inject. So the current that we can inject while we're doing synthetic inertia is limited by the inverter, typically about 1.2 times the rating of the inverter, whereas a big heavy spinning machine can typically provide 4 or 5 times the rated current. There's one little silver lining of that, and that's that we can produce that current for an indefinite amount of time, whereas we have when we have a spinning machine, obviously things start getting hot. So there is a limit to that as well. So how we've gone about this, we've gone about it through really a couple of things that we've done even before starting the trial on site. We did a lot of modeling, PSCAD modeling, and to try to at least get the system operator familiar with what we're going to be doing when we're in virtual machine mode. And we've also been working closely with the Tesla facility in California. I think that's right, Joseph, isn't it? California facility. Yep. Yeah. And they've been running bench testing. Maybe you want to talk about some of the bench testing they've been doing, Joseph?
Yeah, sure. So maybe go to the next slide. Well, I'll go straight into the data. So just to step back a little bit. So Hornsdale is a 150 megawatt generator, and any implementation on what we call virtual machine mode or the grid forming inverter technology. So that is a change in inverter characteristics and does trigger the 539 modification of the GPS, that process. And that's typically, my experience, I've been through a couple now, is a 12 to 18 month period roughly. So what we did at the start of that process was we ran quite a few bench tests, and we did that at the same inverter power stage. And this is our grid simulator in California. So it's roughly each power stage is roughly about 70 kVA. So we've done a few step changes in voltage and in inertia, in frequency. And we modeled that against the PSCAD model in the virtual machine mode to get really confidence in the benchmarking of that. And so what we see through here on the left-hand side, that's the test results itself. So you can see the top left-hand side there, that's the actual voltage step change. So that's from nominal to 0.7 per unit. So you can see it in the cycle, so it's a big step change. And then in the bottom there, we see the actual physical response of the unit. So the physical response of the unit at the waveform level, we see that almost an instantaneous waveform response by reactive current injection. And what we can also see is that here we've done it at a relatively high inertial constant just to show a large response. And you can vary that. The great thing about grid forming inverters is you can vary the inertial constant to whatever you want. We can vary between 0.1 megawatt seconds per MVA to you can go up to 100 megawatt seconds per MVA. And we've done a whole bunch of trials in between that. So what you're seeing here is basically the same thing you see on a synchronous generator in a step change, that resistance of the change in voltage, so by injecting that reactive current. And on the right-hand side there, you can see that's just at the PSCAD study, and we show a very close alignment through there. If we go to the next slide there, Garth, thanks. So here the same test, but we've done a deeper fault, so down to 0.5 per unit. And again, you can see it's top left-hand side is a test, right-hand side is a PSCAD modeling. One of the things to observe through there is we do see, because it's a large step changes and a high inertia constant, we are seeing the saturation of the inverter. So one of the key, in my opinion, one of the key differences between grid forming inverters and synchronous machines is that there is a current limitation on the power electronics, where it's not the rotor magnetics, which is just injecting that current. There is a physical limit on the substrate of the power electronics. So here we have the saturation, so the current will hit limit. That's fine. It doesn't trip the unit. It just means it limits the amount of reactive current we're injecting through. So if you go to the next slide through there. So once we worked very closely with AEMO and Electronet on getting confidence in those bench level trials. And so really the importance for grid forming inverters, you can do a lot of bench level testing, but it's really live data, which is really important. So we rolled this out to 2 inverters, and we picked 2 different inertia constants. One, a very high one, which is not something you'd ever see on a synchronous machine. So H equals 50, and we wanted to do that to sort of really so that when it was actually in service and smaller disturbance events, we could actually measure and see, because that was the importance of that. And then one closer to what we wanted to adopt, which is H equals 5, which is comparable to a traditional gas peaker, which is really what the batteries are replacing in the market. And you can also change the rotor damping as well through there. I'll hand over to you, Garth.
No, sorry, Joseph. I was just going to say, I think at that inertia constant of 5, we'd be looking at providing, roughly, if we roll that out across 150 megawatts, we'd be what, a quarter of South Australia's inertia requirements, something for the
yeah. So the H equals 5 at Hornsdale is about 1,000 megawatt seconds. Yeah.
Right. Yeah. So I mean, we've been running these trials since February, and we've actually captured several events that have happened in that time, and we'll go through those a little later in the slide pack. But yeah, we also, I mean, one of the things, of course, that we have to do when we're running these trials on two inverters on site is we have to meter them. So we've been using these SEL meters, and they're extremely fast, and they've been very good at capturing the events, although what triggers them has also been one of the challenges that we've faced, and we'll probably talk about that in a bit more detail as we go through. Okay, so here we go straight into the results that we've seen, so on the left hand side of this slide, you can see the site response that we get from basically all of the inverters across the site, noting that only a very, very small percent of them, less than 1% of them, are actually running the virtual inertia mode. And so as a result, what you're seeing there is a change of output responding to a change of frequency, which is basically how the Hornsdale Power Reserve has been set since the start. And then with virtual machine mode enabled on those other two inverters, you can see quite a different response to the same event, where you can see that the maximum active power change is actually occurring in response to the maximum rate of change of frequency, and so that's really the big difference between the two. Joseph, do you want to elaborate any more on those?
So really the point to note there is so all batteries operating and then providing FCAS contingency provide a frequency watt-based response. So on the left there, we are purely seeing a traditional proportional response to frequency. So as the frequency hits the nadir, we hit the maximum power export. That's on the one, and so that's the full aggregate 150 megawatts. And on the right-hand side, that's the physical inverter. And as Garth said, effectively what we're seeing is that resistance to change. So the maximum power of the inverter is hit at the maximum rock-off. So by definition, by the time you hit the frequency nadir, the rock-off is 0. So the inertial response is 0. On that particular inverter, we disabled the frequency watt response so we could physically see the inertial response a lot clearer. So that was purposefully done. But in reality, once this is implemented, you'd see a combination of frequency watt and rock-off response, which was really for me the exciting thing. I'll hand back to you, Garth.
And yeah, look, the next slide is the mic drop. This is the Callide event that happened on Tuesday. So we've just thrown that one in there. Joseph, you maybe want to step through our response to the Callide fire.
Yeah. So yeah, this was the Kalide trip event, which was on Tuesday. So I was up late yesterday just compiling the LSPEC data just to really get a taste of what happened. So basically during that Kalide trip was about 2:07 on Tuesday, NEM time. We were in the market at roughly, but AGC took us to about 22 megawatts, Hornsdale itself. And that because we'd lost that 2.4 gig in Queensland, the NEM frequency, and I know there was some islanding in Queensland with a much higher, much wider frequency range. The NEM frequency went down to 49.6, which is a relatively deep contingency event. So on the left-hand side, we see Hornsdale providing roughly 60 megawatts of raise instantly as to that fault. But on the right-hand side, this is probably the key bit for me, is the rock-off. We got roughly about a 0.2 hertz per second drop, which is, in my experience, quite high for the NEM, and a 0.4 hertz per second recovery. So what we see there is on the right-hand side where the 2 is, as that frequency really drops off, so it's way and start leaving the normal operating frequency band. In fact, before we leave the normal operating frequency band, the active power starts getting injected through on the inertia, the inverters with the VMM on. Now, each of those inverters is 500 kilowatts. So what we're seeing there is and this is at a high inertia constant, H equals 50, right? We are seeing the inverters hit to full power as that frequency drops. So effectively what we're trying to do there is arrest the frequency decay and reduce the nadir. And that's effectively where the industry needs to go. But more importantly, what we see is during the recovery, we see the overfrequency swing, which is quite common in contingency events in the NEM. We see that we start to go into an overfrequency in the NEM, right? And there's probably a few reasons for that. There's some unfrequency load shedding, but also some other generators responding. But as we're going higher, we're resisting that change. So now we've actually almost got to full charge, right? So we're trying to resist the NEM going into overfrequency. And so that response is basically out of phase with the NEM frequency. So when we're trying to balance that out, now you have that roughly about 2 second period oscillation in the NEM, and this is really trying to smooth that out, which we thought was a really awesome application of VMM. Back to you, Garth.
All right. Well, I guess, no trial would be complete without facing its fair share of challenges. And we have so far faced a number of challenges. So, one of them is really around the SEL meters, which are absolutely brilliant meters, but they collect an enormous amount of data. But also the events that we are trying to capture here are extremely fast, and trying to trigger the meters to collect the data is very difficult. Either the settings sort of weren't sensitive enough and we were missing events, or we were setting them too sensitive and they were just filling up with data, which was not an actual event. So we've been working on other ways to sort of continuously recycle, I guess, the cache in the meter, and then capture it when something has happened. So make sure that we save the data after an event, and that's been one of the more tricky parts of the trial so far. Joseph, you got more to add on that?
Yeah. I mean, really, Garth, you captured it up. It's hard. It's actually really hard to in an actual full field trial. It's actually hard to catch data which is very small changes. So we are working on distinct triggering to actually launch the SEL meter. We're working actually with SEL themselves to capture this. But the big events like we saw on Tuesday, we can capture that sort of data. It's hard to catch the smaller stuff. But the LSPEC metering, which isn't the same period, but still is a high frequency used for fault recording, that it provides a lot of data as well through here. So there's lots of data, lots of data, almost too much data.
Yeah. And then of course, one of the other issues that we've struck is really with some, I guess, unintended consequences of the hardware and software that really exists. We'll start it as a home-based system, I guess. And so we've actually found a couple of sort of harmonic issues while operating in virtual machine mode. So one of them is associated with sort of probably over filtering, I guess, harmonic over filtering, and the other one is a bit of a frequency wobble that we've seen, which is driven by the anti-islanding. We think the anti-islanding software that's already in the inverter. Joseph?
Yeah, correct. So all of the Tesla inverters which we sell onto the market are actually grid forming, but it's really a firmware enablement to operate them in a virtual machine mode, because the same inverters are operating in backup and microgrid, which is effectively that's all a grid forming application. So effectively, one of the things we do when we go to a current source, and for a lot of grid codes, is we actually have an active anti-islanding, because we don't want to be generating in an island. So we do purposely try and wobble the frequency to see that if it does change to shut down anti-islanding. So that bit now we're disabling on the Hornsdale inverters, because it's not really relevant on those large scale projects. Thanks, Scott.
Yeah, so I guess as a result, this is what we're planning to do. We're doing some new tests with our virtual machine mode on, but we're going to be switching off the SFS, which will hopefully cure some of those issues that we're seeing around harmonics and wobble. So what are we doing next? Next, the whole idea of the Hornsdale virtual inertia trial is to be able to roll it out right the way across Hornsdale Power Reserve, and that includes the original 100 megawatts as well. So we're looking at doing a whole 150 megawatts of Hornsdale, all with this virtual machine mode capability. To do that, as Joseph mentioned, we've got to get through a 539 process. So we've got a few more studies to do, and we are working on a package. We hope to do that later this year, and yeah, there will be a few additional bits of testing that we'll have to do in order to get there. But look, basically we're on track. We're hoping that that this will be rolled out across the full battery in future, and these results that we're seeing, would we think help to stabilize the network in a way that isn't currently being done from large batteries. So it's really taking that next step. With that, maybe questions, or if Joseph has anything to add.
No, thanks, Garth. Great.
Great, thank you, Garth and Joseph. Yeah, I think some really promising stuff. Again, we'll take questions at the end so that we've got plenty of time. So I'd like to now introduce Dr. Behrouz Bourani, who is a senior lecturer as well as the director of the Grid Innovation Hub at Monash University, and will be speaking to their weak grids study. So over to you, Behrouz.
Thank you so much, Carl.
Your slides there, and if you just present.
Do you?
Yep, so we can see your screen now.
Yes, okay, I guess my Zoom had a...
Bottom right. Be able to present. Actually, that's not PowerPoint. Sorry, so I'm probably leaving you astray.
Well, I guess there is a problem. As soon as I go to full screen,
I think we might have lost audio on you, Behrouz.
Carl, do you?
Yeah.
I guess I'm back, right? I had an issue. I don't know what happened. Let me open my slides one more time with another software bit.
Sure.
See if I can. I had an issue with, as soon as I start sharing it, my Zoom actually crashes. Let me start one more time. Is it all right now?
Looks to be there, yep.
Okay, so I don't want to go to full screen. Apparently, as soon as I go to full screen, it I guess you can see the slides pretty well. So let's actually stick to this. Hopefully it won't crash.
Not a problem.
Okay, thank you so much for the introduction. So I'm actually today presenting the project we are doing, this study we're doing for ARENA on stability enhancing measures for weak grids. This is the outline of the presentation, and I try to be quick and actually go through the different tasks that we are doing in this project. So the project essentially is split in 3 different tasks: grid classification and testbed, and the tasks 2 and 3, which are grid strengthening solutions and internal controllers and interactions, which are more interesting for us. So today, what I'm going to do, I'm going to give you a very brief update on the project and what we've been doing, in particular with a focus on grid following inverters and grid forming inverter activities that we've been doing, and also a little bit on activities that we've been doing on syncons to actually help the grid to maintain its stability, in particular in weaker parts of the grid. So let's start with what we've been doing on GFLIs, or grid following inverters, and stability margin for them. I believe it is now pretty well established and well known that these grid following inverters, which rely on a PLL to get synchronized with the grid, they have issues when they are operating in weaker grids, and there are certain problems associated with these weak grids, and we do require, of course, some sort of a index to understand when and under which scenarios we might be unstable. So far, well, people have been using indices like SCR or different variations of SCR, which are not really accurate. You cannot really say whether your inverter is operating properly in a weak grid if SCR is below a given level. It does really depend on the internal controllers that you're having. So what we've done actually so far, we have tried to use Lyapunov theorem in order to understand whether we can define an index for grid following inverters to understand under which scenarios they will be unstable. So we successfully proposed a Lyapunov function, and we found the domain of attraction for this system, and we actually came up with an index, which is an absolute index that can tell you whether your inverter operating in a particular grid will be stable or not. And this index depends on all of the parameters that you've got in your system. It is no longer only looking at the SCR or impedance of the grid. Of course, it takes that into account, but also it takes into account the coefficients of the controller that you've got, the coefficients of the PLL that you've got, and the current control, everything. So it's a combination of all of the factors that play a role, and gives you a very accurate indication of stability of your system. We have I published the results in the paper below, so this is already available in public domain. So if you're interested to know more about this index, you can refer to this paper. Of course, I need to acknowledge here that one problem with this is that you wouldn't typically have access to the coefficients of the controller. But if you are a manufacturer, which should, and you, of course, this is your own PLL and you're developing your own control strategy, then you can use this in order to understand whether it is stable or not. Additionally, what we did, we came up with a compensator for the PLL, and this compensator actually can give you a very robust performance, and it's very, very robust with respect to grid strength variations. What I'm showing here is the phase portrait of an uncompensated PLL at the top and the compensated PLL that we designed. And this compensated PLL can give you a very, very good performance in very, very, very weak grid. SCR 0.25 here, still it is stable, still it won't be unstable with this adjustment that we've done to the PLL. The results of this hopefully will be published soon in a journal paper. But I guess the flavor of the day, flavor of the month is more on grid forming inverters, and we understand that, and we understand that we are actually moving towards a future grid with grid forming inverters. And we have been working on grid forming inverter control to see whether we can actually come up with better control strategies. What we've seen so far today in the seminar has been mainly around this technology here, in which you are hoping to have a grid forming inverter which would mimic a synchronous generator. You're hoping to have control loops which are essentially identical to a synchronous generator, and you can have a damping ratio, and you can have a moment of inertia in your system, and this will be more or less what you will be getting. You can change different parameters in this structure. You can change your damping ratio. You can change your this omega n, which is a function of your damping ratio and moment of inertia, and you can tune your a virtual synchronous generator, and that's fine. And this is what we are doing at the moment in most grid forming inverters. And this would be what you get in an islanded mode of operation. So in the islanded mode of operation, if you want to have a better Rokov, you will sacrifice your transient actually response to dynamic response in your grid connected. And you don't know when you don't know when you will be operating in grid connected and islanded. You can go to islanded and you're expected to still work there. So if you want to have both of actually good performance in both islanded and grid connected, there's always a compromise. So you have to choose what you want to do. What we have been doing, we have come up with another control methodology. I'm not going to go through the details. It is a little bit, it gets a little bit intense if I want to go through all the details of this control strategy. But what I can show is the results that we've obtained. So if you are, the top one is what we have in the grid connected. The bottom one is when we've got in standalone mode. And the blue one is a droop, only droop without any virtual synchronous generator. The red one is virtual synchronous generator. And then the yellow one is what we have designed. We call it Quark. And this is also the standalone islanded mode of operation. If you look at it in the grid connected mode, our response is better than a virtual synchronous generator in terms of when it gets damped and when we reach actually a steady state, while we have better Rokov performance in the islanded mode of operation. So it's actually, it's better than the VSG in both scenarios, both in grid connected and islanded. And with only a VSG, like what we have seen in different installations, VSG alone won't be able to give you both performance perfectly fine. But this is what we have actually proposed here, is giving better performance in both islanded and grid connected mode. Now, of course, this might be a little bit difficult to design. The design procedure is not easy. We acknowledge that. And we are working on a better, actually, another variation of this method that is based on an analytical approach. So you can write maybe only a few lines of code, and based on a few equations, you would be able to come up with this controller here, which would be your active power controller in your grid forming inverter. And it can give better performance, even better than what I just proposed by a tweak. Stay tuned. All of this will be published very, very soon, and we will publish them on our website, and of course they will be accessible online via probably IEEE most likely. Now, another aspect of grid forming inverters that we've been working on has been their transient stability improvement. I was very actually happy to see when Sachin was introducing the results that they had some oscillations upon fault clearance. That's actually a problem in grid forming inverters. If you do not properly damp your system upon a fault, I mean, when you're recovering from a fault, you might have some oscillations, and these oscillations can have different reasons. If your controller is not properly tuned, or if you're operating a weak grid. So these are the oscillations that you might get depending on your grid strengths, depending on your controllers. You will have these oscillations, and they will die out eventually, but you won't get a fantastic result. So what you can do here, you can have a virtual resistance added to the control loop in order to get rid of these oscillations. And what we have done previously, mainly people, when they put this virtual resistance, they put a constant virtual resistance and then they phase it out. But what we have done, we have come up with a methodology to have an adaptive virtual resistance. So when the fault actually recovers here, we adaptively change this virtual resistance in order to support our inverter, the grid forming inverter, to recover from the fault without excessive transient. I have some results here to show you. So this is when you do not have any virtual resistance in the network. You actually recover from the fault and you have these oscillations, but with the virtual resistance that we have proposed, you almost don't see any excessive transient, and very smoothly you will recover from the fault, and you won't see any oscillations that are sustained in the system. Also, this one will be published. It is under review, and I believe the results can be accessible within a month if everything goes well. And you will be able to find the paper on IEEE. And of course, we will publish all of these on our website, and I'll introduce the website at the end of the presentation. Last bit that I would like to have a quick I talk about is SYNCHRON control and allocation that we've been doing. We acknowledge that in addition to grid forming inverters, still a great deal of discussion is going on about synchrons, and we want to know whether we can better control synchrons or where we should allocate them, what size we should actually have for these synchrons. The synchrons that we have been we have been working on has been using an exciter AC1A, and then this SYNCHRON, actually what we have done so far, we have tried to come up with a better exciter control for our SYNCHRON. So the results show that if you manipulate the controller of the SYNCHRON rather than only having a simple first order controller, if you come up with higher order controllers, it can significantly improve the performance of the SYNCHRON, in particular in weak grids. And then also what we have done, we have also been trying to understand where we should actually allocate these SYNCHRONs, and where we should allocate and actually which size of the SYNCHRONs in the network. So two studies have been done. So I can actually categorize them, one into the optimal allocation and sizing. We've done two sorts of allocation and sizing. One is using heuristic algorithms, will probably not give you the best result, but we have actually extended the results, extended the studies to a convex optimization approach. And we are almost done with this study. We have presented the results to our partners, and we will very soon also publish this on our website. So you can actually have a very nice procedure to size and actually allocate your SYNCHRONs in the grid. Another study, like I said, is a exciter controller for SYNCHRONs, and the exciter that we have designed outperforms the existing and conventional exciters, and it can give you much better performance in weak grids. Also, the results of this one will be published very soon, and all of them you can find our website. Here is the website that we've got for the project. All of the papers and publications and reports will be appearing here over the next couple of weeks and months. And the project, of course, is running for another year at least. And you can see the reports here. Now, as future steps, what we are hoping to do, we are hoping to apply the allocation mechanism that we have had to grid forming inverters as well. We are very keen on looking into transient stability of grid forming inverters, like what we did for grid following inverters, and applying nonlinear control theory to grid forming inverters, and see how we can actually determine the limits, and also interaction analysis of inverter-based resources. This is extremely important for us. We are hoping to use impedance-based analysis and black box identification. So we identify the impedance of our inverters as a black box. We don't need to know anything about the inside control. And based on that, we are hoping to understand interactions that might happen in the grid between the IBRs in the system. This is very interesting study, and stay tuned for results for this one. And finally, another project that I've been working on has been a PLL-less grid following inverter. So this is almost there, and we do have very good results for this one as well. So the idea here is to have a converter that connects the point of the grid without measuring any voltage from the grid, without having access to the point of connection voltage, without measuring the grid voltage. It can inject any real reactive power that you want. Of course, this is different from grid forming because it's not controlling any frequency, or it's not controlling any voltage at the point of connection. It just injects the power that you need without any need for any PLL. So no PLL is used, and essentially you can look at it as a power synchronized or current synchronized grid following inverter. Okay, I guess that's it, the presentation. Thank you, Carl.
Thank you, Behrooz. Really great and detailed investigation of many of the finer points of these problems. Look forward to the publication of those results.
Sure.
I think there'll be lots of interested parties that we can send your way and
absolutely
get those results to them. So up next, I'd like to introduce Meliti Gunawardena. She's the Principal Engineer in Network Planning and Operations at Transgrid. We'll be highlighting their Walgrove battery project. Thanks, Meliti. Okay, I've got your screen now. Excellent. All good to go, Meliti? Might have lost audio.
Hey, Meliti, I think your microphone might not be working. Do you want to just check your settings there?
How is this working? Are you able to hear me now?
Yep, we can hear you. You're just a little bit quiet.
Let me just double check on my audio settings.
That's much better.
Yeah, okay. It might take a while. Sorry about that.
Not a problem.
But, I'm hoping you can see my screen. Yeah. Thank you very much, Carl. So I would I'm going to be providing an overview and an update on Transgrid's Walgrove Grid battery project. So I guess just to give you a bit of background on why Transgrid embarked on this project. As we all know, the generation portfolio is continuing to evolve across NM as we have more inverter-based renewable sources replacing our coal fleet. So in the context of the New South Wales system, over 30% of our coal-fired generation capacity is scheduled to retire in the next decade or so, which raises both energy security and system security challenges for us. So in terms of the system security challenges that we're facing, based on the scheduled retirement dates of plants in New South Wales, we expect that we will be looking at system strength remediation in the late 2020s, and that there will be an inertia shortfall in the early 2030s. So this is purely based on these asset retirement dates, but it is also understood that these system security challenges could come earlier due to market conditions. We see that the production from the coal units are becoming increasingly intermittent in response to low wholesale prices, particularly when the renewable resources are abundant. So this leads Transgrid to believe that there will be an inertia gap declared for New South Wales well before 2030. Under the national electricity rules, TNSPs have the responsibility to source solutions for inertia at the time AEMO declares an inertia gap in the region.
lost.
Are you able to see my screen? I'm sorry.
Yeah, we can again.
Okay. The slides is what you're seeing. I'm just not sure because it stopped. It seemed to have frozen.
Okay.
Yep, we've got the battery storage as a solution slide up at the moment.
Okay. Yep. Let me just get back to it. So under the National Electricity Rules, TNSPs have the responsibility to source solutions for inertia. Like I said, at the time, AMO declares an inertia gap in the region. So as part of determining how best to address the inertia requirements in a cost-effective way, Transgrid is investigating new technologies to meet these challenges. So in particular, I think we've identified batteries as an emerging solution with the potential to support frequency control in the future, but also in satisfying the secure level of inertia requirement. So compared to traditional technologies like synchronous condensers, batteries can offer multiple complementary uses and are expected to be low-cost solution for customers given their ability to provide both market and also network services. So this allows the cost of the investment to be shared between networks and generators, reducing the potential cost burden for the customers. So I guess this paves the way to Transgrid undertaking the Volgro Great Battery Project with joint funding from both ARENA and the New South Wales government. The key objective of the project is demonstrating the use of grid-scale battery with advanced inverter capabilities to provide not only fast frequency response, but also synthetic inertia services to the New South Wales transmission system. The project, our expectation is that the project will serve as a pilot project to show whether a grid-scale battery can be used to effectively address the emerging inertia gap in a cost-effective way by supporting a cost-sharing model between networks and market participants. But since this is the first grid-scale battery in New South Wales, for Transgrid, it is also an important learning process in terms of understanding the technology, the limitations as well as the capabilities, and also the complementary services it can provide to the network. It will also provide us, the Transgrid's planning team, with better data to support future battery projects connecting to the New South Wales network. So just to give you an overview on the Volgro battery. So the project will be trialing the use of a 50 megawatt lithium-ion battery with 75 megawatt hour energy storage capacity. And it'll be connecting to the 132 kV bus at Transgrid's Volgro substation in Western Sydney. So the Volgro substation is ideally located for the Sydney region on a strong, unconstrained part of the network. The battery will be designed and constructed by Tesla using 36 Tesla Megapack units with the synthetic inertia capabilities enabled using the virtual machine mode. Transgrid will be owning and operating or maintaining this battery, but we've appointed Infigen Energy as the market intermediary who will undertake all market functions. So this will ensure that the full capacity of the battery is optimally utilized, which in turn helps provide network services at the lowest possible cost to the customers. The part of this project is demonstrating that it is possible to deliver the required inertia services while we undertake commercial operation. So I won't delve too much into the virtual machine mode, as this was already covered by Garth and Joseph in detail in the previous presentation. But as Garth mentioned earlier, the virtual machine mode of Tesla inverters uses specialist firmware to mimic the swing equation that governs the rotor dynamics of a synchronous machine. So as the inverter's inertial response is created by the inverter controls, the response is configurable and can be modified based on based on the network's need. So this is an advantage over traditional synchronous generators that that have a fixed inertia constant based on their mechanical or the physical characteristic. But obviously, the bottleneck for the inverters is, as mentioned before, is the current capability limitations. For the Walgrove BESS, this virtual machine mode will be enabled as part of stage 2 of the project via 539 process. In terms of where we are at with the progress of this project, overall the project is progressing well and is on track for commercial operation towards the end of this year. So we achieved a major project milestone in early May with the approval of performance standards and the issue of 534A letter by AEMO and the subsequent execution of the connection agreement. Walgrove is in fact the first battery to reach the committed status in New South Wales. Looking ahead, registration of the batteries is expected to be achieved by August this year to enable the commissioning process. So we're looking forward to testing this battery and having the battery operating in the network in grid following mode by October. And as I said before, stage 2 of the project will then be enabling and testing the virtual machine mode, which will be started around November to December this year. But beyond this normal generator connection and commissioning process, we also plan to have an ongoing performance monitoring and testing process for the Walgrove battery. So we'll be monitoring the performance of the BESS over a period of time and measuring the battery response to actual system events. So typically a system event likely to invoke a response from an inertia source like this one would be a considerable frequency deviation like what we experienced a couple of days ago, a loss of a large generator or a load or a system separation event. While these kind of events are not very common, we should be able to capture the relevant performance data as Garth and Joseph presented previously, and that should be enough to give us a clear picture on whether a sufficient inertia response is being delivered by the battery. So as part of the on-site installation, we will be installing monitoring equipment at appropriate locations at the site, so covering data from the network side, the 132 kV connection point, and the terminals of Megapack units. And our expectation is that following a trigger event, the data that's captured from these sources can be used to replicate the network model at the time of the trigger event, and then we can simulate the best response operating in the virtual machine mode. So the intention is then to compare the actual performance of the battery to the simulated performance and to assess whether the overall performance of the battery is in fact in line with the expectations. This would give us an opportunity to assess the impact of the state of the battery in terms of depth of its charge and discharge and the behavior of the BESS leading up to the event on the inertia services that it delivers. So we expect that the learnings from these performance monitorings then can be used to support future system modeling work that we undertake in New South Wales, and also to inform future contracts to ensure that there's enough headroom available in the battery to provide required network services when it's needed. It would also improve our understanding of the capabilities and the limitations of the battery to address some of these emerging system security challenges, hopefully with transferable learnings across the NEM. So that's the update that I have on Walgrove today. Yeah, looking forward to address any questions anyone might have in the panel discussions.
Thank you, Meliti. So we're going to now open it up to questions from the audience. We're about 20 minutes now. So I'm just going to go through these based on the popularity in the chat. The Q&A window there. So if you are keen to hear any in particular, feel free to upvote those. I think I'll just go through them and try and guess who they were directed to. But the first one here I've got from Jahan Paris is the VM virtual machine mode relying on external measurements. Perhaps for Garth and Joseph.
Yeah, maybe, yeah, it's Joseph Tesla. Maybe I'll answer that one. Garth, he may have the understanding of the system architecture, but no, it doesn't rely on any external measurements. This is all happening at the inverter level.
Great, thank you for that. So the next one is from Daniel Gilbert. Why do you not keep the inverters in virtual machine mode all the time? Why wait for a contingency event or to change modes, or perhaps that's just the way the VMM is being described?
Yeah, no, look, I think that the truth of it is that inertia isn't always a good thing. And so what we're trying to do is get all of the best aspects of having inertia in our system, which is responding to that rate of change of frequency without necessarily moving all the time. You know, we've got an already complex system, and if everything was moving all the time in response to each other, there is a chance that you get a lot of interaction between control schemes. So it's always a delicate balance.
Great, thanks again. I'm going to immediately contradict myself and move beyond the popularity, because lots of questions for Garth and Joseph, so I'll be a little bit more democratic. There was one for Meliti. Who would be operating Transgrid's, the Walgrove battery commercially, given the National Electricity Rules ring fencing provisions?
Yeah, so Infizen will be operating it commercially, so bidding into the energy market and the FCAS market. Yeah, Transgrid will be owning and maintaining the battery, but Infizen will be operating it commercially.
Great, thanks for that. So another one from Edward Burstinghouse to Dr. Barani. What order of model do you use for the network when designing the controller using the H-infinity method? Is the network model linear?
Well, what we have actually done so far, essentially, we've focused on SMIB models for the system that we've been looking at. So we've designed for the moment a controller for a SMIB model, and we tested in this SMIB model. It works perfectly fine. And what we're doing at the moment, we're actually taking that SMIB model and actually putting in the West Mara region. We're hoping to actually do these tests in very near future to see how our inverters would operate in the West Mara region. So we do have the whole PSCAD model for that area, and we are hoping to see that. But to answer the question, the design procedure so far has been based on SMIB model, and typically I think this is not a very unrealistic assumption to model your system with an impedance and an ideal voltage source and the dynamics that you will be seeing. Of course, there are impacts from other inverters there, and these are the type of things that we are hoping to see with the impedance-based analysis that we are hoping to do also very soon. But yeah, the very short answer is that so far it's been only on a SMIB model, and we are hoping to extend these studies to a larger model to see how the system would operate.
Great, thank you for that. So I'm going to go back up to one from Carl Christensen. So again, for Garth and Joseph, should batteries be set up to provide both FCAS and synthetic inertia simultaneously, or should these services be provided by separate batteries? If a single battery energy storage system is providing both services, which service should take precedence? I think also if other panel members have got responses, feel free to chime in as well.
Right. Well, yeah, maybe I'll kick off, Garth. You can maybe jump in. But my opinion on this is that for batteries to be successful commercially in the NEM, they need to provide a value stack service. So they need to provide multiple services and have those revenues from multiple services. So there's no reliance on external funding, and they'll all operate independently in the NEM. That's ultimately where we need to be as an industry. So I think inertia services and frequency control services, or primary frequency control services, definitely should be provided in parallel, and they are in fact complementary. So if you think about the example we went through of a typical contingency event where we have a decay in frequency, which is traditionally the inertial market. So that's a rate of change of frequency. That's when the inertial response dominates. But when we get to the frequency nadir, and as that rock-off reduces, so as we reduce our rate of decay, that's when the frequency watt, or the primary frequency control, takes over. So at the bottom of the nadir, the rock-off is 0, but the total frequency error is at its maximum. So frequency watt response is maximized. So in a way, it's a blended response, so to provide the early initial response and the maximum response to once it's at the highest frequency error. So technically, in my mind, it should be definitely combined. Garth, I'm sure you think the same.
Yeah, no, I feel exactly the same way. Look, we've got layers of control schemes all on top of each other in the battery, and I think part of the last 3 years of operation has been really refining and making sure that it's providing the right response under all of the different kind of circumstances that you can have. So all of these things that we can do, you need to be able to do them at once, but you need a control system that's that sort of has some overarching things happening in there, so that the most important responses are happening at the right times.
Great, thank you for that. So I've got a question here from Daniel Gilbert for the Read the PowerLink presentation. So did you model using grid-forming inverters as the renewable generation inverters? This is instead of having a separate BESS-based grid-forming inverters. I'm hoping the future of RE dev is with a grid-forming inverter rather than grid-following and separate battery energy storage systems.
Thanks, Daniel. A good question. So in our project, the grid-forming inverters had the battery, so it was a separate. So the IBRs were grid-following. Because at this stage, to our best knowledge, we don't have any manufacturer providing a solar farm or wind farm in grid forming mode. But I also hope same way that in future we move towards where solar farm and wind farms with some combination of battery or some other technology can be grid forming itself. So we share the thoughts. Thanks.
Great, thank you for that. So I'm just going to go back up the top here. Question again for Joseph and Garth. What was the scope of the PSSE modelling as part of the National Electricity Rules 5.3.9 for the upgrade?
Yeah, maybe I'll answer that one. So I guess the scope, so any change to an inverter characteristics basically triggers a 539, and the 539 package is the full scope of studies, both on PSSE, which because it's an RMS-based modelling package is less useful, and the majority of the work is really on the PSCAD study. So and this is kind of an issue for the industry, I think, because once you agree on the inverter characteristics have to be locked to an inertial constant. So once you pick a inertial constant, the connection package has to be done. All of those, hundreds of cases need to be done on that.
Yeah, and this is a limitation right at the moment, because I think we're going to need to improve on this in future. There will need to be tuning, I think, of these inertia constants once we have lots and lots of these machines all providing an inertia response.
Great, thank you once again. So I've got a question from David Letch here. In a very low physical inertia grid, how do the grid forming inverters manage the overall system frequency? I guess that's to anyone who'd like to have an answer.
So I can actually maybe add a few comments here. So, well, of course, the grid forming inverters themselves, they can provide inertia for you. And then, so if you don't have physical inertia, that's fine. If you've got the grid forming inverters, they can be the source of inertia. They can actually provide the frequency regulation for you. So I don't see a lot of problems here. And while I'm actually answering this, I would like to also make a comment on what we can have as the controller for grid forming inverters. converters, they don't necessarily have to mimic exactly what we've got in a virtual in a synchronous generator. So we, of course, yes, we know that synchronous generators, we've had them for many years and they're working fine, and it probably seems natural to actually follow what they have been actually delivering for us, but we don't necessarily need to do exactly what synchronous generators have been doing for us. Inverters are a lot more versatile, a lot more flexible than a synchronous generator. A synchronous generator is fixed and it's actually bound by its structured physics, and it cannot do much more than what it is doing at the moment. But inverters are very flexible. So we should not actually focus only on synchronous generators and say that, okay, this inverter has to do exactly what a synchronous generator has been doing for us. I believe what we need to do to be able to have a grid which is based on only power electronic converters, we should go beyond synchronous generators. We should think beyond synchronous generators and see what else we can do that synchronous generators could not do for us previously. Now we've got this device which is fully flexible, fully controllable, can give us any voltage waveform that we want at its terminal. So let's take advantage of this. Don't focus only on mimicking synchronous generators. So we probably should think about what else we can do. What alternatives are actually here that we could do to have a better control in our system. And that also goes to the virtual inertia here. We necessarily don't actually look at, we shouldn't necessarily only look at inertia here. So inertia has been a mechanism that we've had in synchronous generators that would help us to maintain frequency, to arrest that nadir, to actually have better Rokov, but it's not the only way of controlling frequency. So there are other alternatives that we should look into them, and we should not limit ourselves to virtual synchronous generator. But to give a very short answer, I guess inverters are very well capable of providing inertia, even if we don't have synchronous generators in the grid. So there should not be a problem in that sense.
Thanks, Baruz. Sachin from PowerLink. I would just want to add to what you have said. Fully agree with what you have said. In general, at least in my opinion, any inverter connected plant is more stable than a synchronous plant in general, right? And we should make good use of that stability that is provided, because we don't have any rotating mass there, right? And let's be open here. In a very weak grid, when a synchronous machine is connected, and when we have a disturbance, the oscillations of the power oscillations of machine itself cause a problem. So here is an opportunity with the inverter. How do we balance this out? So I fully agree with Baruz that we shouldn't be just blindly following that. Can I make an inverter to mimic the synchronous machine 100%? We take the best part of synchronous machine, but then we should not forget the best part of the inverter connected plant as well.
Great, thank you for that. Would anyone else like to add to that? Might move on then. I've also become Andrew Williamson now because I lost power on my computer. So there's a question again from Aliti. How was the GPS treated for Walgrove as an asynchronous machine or synchronous? Also, was an FIA required?
So it was treated as an asynchronous battery storage connection, but also because in this stage 1 of the project, Walgrove is a grid following inverter. It doesn't have the virtual machine mode enabled, so it was just a another grid following battery inverter, I guess. I guess because there's going to be a proposed rule change on integrating energy storage into the NEM. So certain questions that we have on this virtual machine mode and how it should be treated in the GPS in terms of the process like 5255. I think some of these questions might be answered in that rule change. In terms of the FIA, I don't believe an FIA was required or identified in the preliminary impact assessment because this is connecting to a very strong bus in the Sydney region. So it was not identified as required.
Great, thank you, Meliti. So I'm going to move on to another question from Edward Burstinghouse. So regarding the tuning of grid forming controller parameters to address instabilities, the question is, how does one know in general the extent of the robustness of those tuned parameter values to other interactions / instabilities that might show up in future as other, assuming IBRs become connected?
Thank you, and I'll take that question, Sachin from PowerLink. It's a very good question, and we face this problem even now. It's not only related to grid forming. So from TNSP point of view, how it is dealt. So whenever a plant is designed, there are certain parameters are proposed, and when those parameters are proposed, manufacturer need to be very satisfied that with those parameters, the internal control of the plant are stable. So there are few steps of this, that any settings that is put into the plant must not be chosen without consulting the manufacturer of the plant, because they know the best about their plant, and we must be consulting with them that can this plant handle these settings. Once we have confidence that, okay, from plant side, we got reasonable confidence, then move to the network side. And yes, we tune a parameter to mitigate one problem, and it's very often it causes problems somewhere else. And hence, the wide scope of the studies are very, very essential for project specific, and therefore the settings chosen for one project should never be automatically used for another project. We can start from there, but the tuning and the settings must be chosen for a project specific, right? No matter how many of those plants have connected in the grid, every location is different. And it's just the scope of wide area studies that gives us confidence that, okay, we have checked this change in the settings for hundreds of scenarios, and we have reasonable confidence. And as an engineer, I would say we'll always have reasonable confidence. We will never be 100% sure that it's a bulletproof. And hence, as system evolves, there's always need to retune, go back to the system and retune the plan to make it useful for future. It won't be just tuned it once and forget it. I think we are out of that era.
Great, thank you for that, Sachin. So I'm going to go to our last question, I think, for the session from Gabrielle Kuiper to Dr. Bharani's excellent point regarding sort of grid forming inverters being more flexible. We've focused largely on providing system strengths sort of in the current system where synchronous machines still exist. So what is the long-term prospect of moving to a zero inertia system, and how will grid forming inverters assist this?
Well, I guess this is of course, this is a fantastic question, and this is very difficult to answer because this change will happen over probably 10 or 20, maybe 30 years, and it will take some time before we reach a point that we won't have any synchronous inertia or synchronous generator in the system. So it's very difficult, and the technology will evolve to reach to that point, and a lot of things will happen. But one thing that I can say here is that if you look at, for example, a microgrid, only like imagine a microgrid somewhere which is not connected to the grid, and it can very easily and reliably operate using only power electronic converters. We already have the existing controllers that we've got for grid forming inverters in microgrids. You can have droop control. These inverters can share power very easily. Virtual synchronous generator can also be added there to actually satisfy all the requirements. So the technology is already there. So we can see that it is possible, but the transition, because we have so many synchronous generators still in the grid, they won't go away very quickly. It's very difficult to say what exactly the NEM, for example, would look like in 20, 30 years from now. The only thing that we can say is that, yes, we do have the tools. We do have actually what it takes to be there. But if I want to just have one prediction that what's going to happen in 20, 30 years, my prediction is that we will be having, let's say, if we've got around 40 gigawatt load that we need to actually service, we probably will have something around 40 gigawatt of wind, 40 gigawatt of solar, and 40 gigawatt of batteries in the grid. This is just a prediction. I don't know how exactly will happen, but I believe this is where to go, and I guess this will this probably will work, and this probably will be something like similar to this arrangement. But yet again, it is extremely difficult to predict, and you don't know where exactly the technology will take us, but I strongly believe we do have the tools.
Thank you.
Behruz,
Behruz.
sorry, Sachin again here,
Yeah,
and it's for the whole group to think, like, once we move to the grid where everything is inverter based, how much do we really care about the frequency of the grid? Yes, we can't go to 25 hertz, but the flexibility of maintaining frequency, it should give us some more flexibility. Like if grid goes from 50 hertz to 48 hertz, if everything is inverter connected, is it really a problem? So that's, I think we need to think there as well. It's a problem only when there is a one plant which is synchronous and everything else is renewable connected. That's the biggest challenge in my mind.
Correct. I totally agree with you. We don't necessarily have to have this extremely tight regulation around 50 hertz. If everything is inverter based, it actually relaxes a lot of things. Totally agreed.
Thank you. Joseph, were you going to add to that?
Yeah, I was just going to add, I mean, when we think about synchronous generation, it's also important to think about synchronous load, because they're effectively doing the same thing. So even if we stopped tomorrow having any synchronous generation on the grid, there'd still be a significant amount of synchronous load, which is effectively providing that inertial support as well.
Great, thank you. I think unfortunately that's all we're going to have time for today. But I think it's been a really great discussion towards the end, as well as hearing from a number of our projects as well as the market bodies. I think we've heard some great and different perspectives on a variety of different topics. It was good to hear about the comparison with synchronous condensers versus batteries, and looking forward to the results of the various projects coming out, particularly watching Wargrove and what happens there. So I guess I'd like to extend my many thanks to the presenters for making their time available, as well as yourselves, the attendees, for sticking around and asking such great questions. I'm hoping that what you would be able to do, you should have an email in your inbox now with some questions about the event. Always hoping to improve on what we do here at ARENA, so we'd be most appreciative if you could answer those emails. So I've got a little bit of background noise, but and then finally, I've got a little slide up here. Just 2 seconds. Sorry, I'm having changed computers. We've also got a variety of different ways that you can get in touch with us at ARENA. So, hang on. Oh, there it is. Thank you. So yeah, please do reach out. I think there'll be some information that's desired by attendees, and we'll do our role and get that to you. But also there's those other. So there's the Insights newsletter, as well as the Knowledge Bank. We've got our podcast there, and I'm told a new season is coming up soon. And then finally the blog at ArenaWire. But yeah, again, thank you, and hope the event was useful and informative, and enjoy the rest of your day. Cheers.